In this video, we're going to take a look at reactions of amines. And the first set of reactions we're going to take a look at is making amine salts. Now, in a previous video, we learned how to name amines. And so the first amine here I'm going to show you is methylamine. Methylamine is a methyl group. There's a methyl group with an amine group here attached to it. This is methylamine. Methylamine, and if you remember from the previous video, that an amine has this lone pair up here, and this lone pair is electronegative. So I'm just going to put this here electronegative like this. So that has a high density of electrons. It kind of has like a negative charge part of that molecule. Now, we can take this molecule and we can react it with an acid. So if we react it with an acid, I'm going to go like this here, and reacting it with an acid, say HCl, hydrochloric acid, and if we do that, then what's going to happen is this hydrogen and this chlorine are going to break apart from each other. And the hydrogen, which is going to be positively charged, is going to be attracted to the nitrogen here. It will attach itself to the nitrogen. And then that's going to make this overall molecule positive. So over on the other side here, we're going to have our methylamine, like this. And then we're also going to have this hydrogen attached. So I'm going to change this from H2 to H3. And I'm going to put a little positive sign on there like that. So we've added that hydrogen. And then this chloride ion over here, the chloride ion is going to be attracted. Now the chloride ion is negative. This is positive, like this. And so they'll be attracted to each other. And so now this becomes what we would call a salt, okay? And so we started out over here with an amine. Over here we're going to have a salt. And so for naming this, what we're going to do is we're going to take the positive side first and then the negative side second, and then we're going to add ammonium to it. So this becomes methyl because that's the positive side here of this molecule, methyl ammonium and then the negative side, or the anion side here, is added next, and so that would be chloride. Methyl ammonium chloride. And this process of adding this hydrogen ion onto our methylamine is called protonation. Protonation. And we could go in the opposite direction like this. Take it back the other way. And if we take it back the other direction, instead of adding an acid, we would add a strong base, such as sodium hydroxide. And if we add a strong base like sodium hydroxide, what's going to end up happening here? Well, we're going to end up then breaking this apart. And so as we come back over this way, as we come back over here, we're going to take our OH. Our OH is going to attach here with the hydrogen that was added here. And so we're going to take the hydrogen and the OH, and over here we'll have HOH, or water. And then the sodium here, the sodium is going to be attracted to the chloride ion, and we'll end up with NaCl, like that. And then what's left over? If we remove a hydrogen and a chlorine here, then we're going to end up then with what we started, our methylamine. Now this process here is the opposite of protonation. It's deprotonation. Deprotonation. Now you might be asking yourself, why on earth would anybody want to protonate or deprotonate? Well, why would you want to do this to an amine? And I'm glad you asked that question. So let me show you a molecule here. Here's a new molecule that we've not seen yet, and this structure may not mean anything to us at this point. And I'm going to write out the name for this molecule. It has a common name, so it's not using the IPAC nomenclature here. This is phenyl ephrin, H-R-I-N-E. Okay, phenylephrine. Phenylephrine, again, may not mean anything to you. Now, this molecule is not soluble in water. In other words, it's not very polar. And so it doesn't really have much of a therapeutic effect. We need, oftentimes, medications to be soluble in your blood. So if you take a medication orally and you want it to get absorbed into your blood supply, it has to be water soluble. And water, we hopefully remember, is polar. And so you need the molecule to be polar. And this isn't terribly polar. But if we treat this molecule with hydrochloric acid, so if we treat this with HCl, so plus HCl, like this, with HCl. So what ends up happening if we do that? Well, if we recall, there is a lone pair here, like this. There's a lone pair right there that's electronegative. And so we can break apart this HCl. The hydrogen will be attracted here to the nitrogen. And so this becomes NH2. So I'm going to go like this, NH2. And we have a little plus there, like that. Okay, that makes this positively charged ion. And then over here, that's going to be attracted to the chlorine from the HCl, like this. Okay. Now this molecule becomes phenylephedrine hydrochloride. Now that's not the IUPAC name, that's just a common name because this molecule was figured out or named long before scientists got together and figured out the whole naming convention. Now phenylephedrine hydrochloride goes by some other names that maybe you've heard of. It's the decongestant in Sudafed and Theraflu and in Dayquil. Okay, and so a decongestant, this molecule needs to be absorbable into the blood and into the blood supply so it can get to where it's needed. And by reacting the phenylephedrine with hydrochloric acid, then makes this into a salt, which is then soluble in the bloodstream and can then go to where the bloodstream wants to take it and have its therapeutic effect. Now here's another molecule we may not have seen before. This is atropine. Now atropine comes to us from the belladonna plant. And belladonna, that's Italian. Bella means beautiful, donna means woman. And the belladonna plant has kind of an interesting history on it. And that's supposedly women in Italy who wanted to attract a guy would take the seeds from the belladonna plant, squeeze them, get the juice out, and stick it in their eyes. And this is a vasodilator. And so it would cause the pupils to dilate. And as a result, they'd end up with these big pupils. And this was thought to be attractive. And so this is belladonna, beautiful women. Now, as it turns out, a little too much atropine can actually make you blind. And so, not actually so good for you. Okay, so that's just kind of an interesting molecule, you know, and it's found naturally in plants, and it has some medicinal uses as well. Now, this is called an alkaloid, and an alkaloid is a nitrogen-containing compound that's found naturally in nature, and it tends to be bitter. And this is good because alkaloids tend not to be good for you. So this belladonna, if you were to eat it, wouldn't be so good for you. Now, one of the curious things about atropine is it's very similar to another alkaloid that's found in nature. And so if we just rearrange this just slightly, just doing a little bit of chemistry here, if I were to change this down here, like this, okay, and just go like this, and attach it like that, okay, and then up here, if I attach C double bond O, and then O, and then CH3, okay. Now this molecule here is fairly similar to atropine. It is an alkaloid in that it's found in nature. It has a nitrogen atom. It has a bitter taste to it, although you might not know that. And that's a good thing because this is cocaine. And this molecule is what we would call free base cocaine or crack cocaine. And this molecule here is not terribly soluble. So if you were to treat it with hydrochloric acid, then you end up with a slightly different molecule where we end up attaching a hydrogen up here to our nitrogen. So we add a hydrogen up here, like here, that makes that positive, and then that's going to be attracted then to the chloride ion in hydrochloric acid. And so this right here would then be Cl minus, like this, okay? And this right here would be the other form of cocaine. This would be like the powdered form of cocaine. And this is much more soluble. This is the type of cocaine that people would then snort. And so that's the difference between the two different types of cocaine. This is the type that is a cocaine salt. It's been treated with hydrochloric acid. It is water soluble and you can inhale it. Whereas the other is the crack cocaine that is not soluble in water, and people would heat it up and then inhale the vapors. Now, one of the curious things about crack cocaine, and which is the free base cocaine, and this is the amount of time you would spend in jail. Curiously, the powdered cocaine, this version of cocaine, you would spend less time in jail than you would with the crack cocaine. You might ask yourself, well, why is that? They're both cocaine. And one interpretation of this is that treating the cocaine with hydrochloric acid takes a little bit more effort. It's a refined product and it's more expensive. And so the people who tended to use this were people that tended to have more money and tended to be white. Whereas crack cocaine users, oftentimes, but not always, tended to be minorities. And so people would use cocaine, just different versions, and one person would spend more time in jail than the other. And guess who that would be? It's generally minorities. And so it kind of raises the question as to whether or not there's prejudice in our laws and such. And when we take a look at these, chemically, they're both cocaine. They're both cocaine. You get high off of them. They're just slightly different, and one is a little more accessible to certain groups than was others. It's just kind of a curious connection there between chemistry and perhaps our drug policies. The last type of reaction we're going to take a look at for amines is alkylation of amines, or actually just making an amine. And so we have primary, secondary, and tertiary amines, and how they get made is really just the same. And so we're going to start out with making a primary amine, and then I'll show you how to turn it into a secondary and then a tertiary amine. So getting us started here, we'll start up with ammonia. Ammonia plus an alkyl halide. CH3CH2Br and a base. Like this. And when we do this reaction, what's going to end up happening here is we're going to remove a hydrogen from here, and we'll remove a hydrogen from here. It will then connect with the OH here and form water. And so over here, we'll end up with water. And then the sodium over here is going to then react with the bromine here, or come together and make sodium bromide. So that'll be NaBr, sodium bromide. And then what's left over is we're going to be attaching this ethyl group onto the amine group here, or the ammonia here. Okay, so then our product then becomes CH3CH2NH2. And the name for this, naming these amines, is going to be ethylamine. This is just one word, and this would be a primary amine, and that is to say there's only one carbon group coming off of that nitrogen. Now, if we wanted to take this primary amine and turn it into a secondary amine, we'd do the same thing. So I'm just going to take this molecule, bring it right over here, and I'm going to go CH3CH2NH2, and then I'm going to react it here with CH3Br, okay, and we'll do this with the same conditions, NaOH, like this, and the same thing's going to happen. We're going to end up bringing our sodium and our bromide ions together, and our hydroxide and the hydrogens together, and what we'll end up with then over on the other side is going to be a secondary amine. So CH3CH2NH, and we'll end up then with our products of water and sodium bromide over here, okay, and CH3. Okay, so this methyl group came over here and attached onto this nitrogen right here. And so the name for this one here now becomes N-methyl ethanamine. N-methyl, so the methyls attached onto the nitrogen, ethan, 2 carbons, amine. And we can take that molecule and we can turn it into a tertiary amine by running it through the same reaction again. So I'm just going to take that molecule, I'm going to bring it over here, give myself a little more space this time here. We'll go CH3CH2NH3, and then we're going to react that then with CH3Br, like this, and same conditions, NaOH, and same thing's going to happen. We'll end up taking a hydrogen off of here, combining it with our hydroxide, giving us water. And we're going to take our sodium and our bromine here, bring those together, give us sodium bromide. Okay, and then we're going to take this methyl group and we'll attach it onto the nitrogen over here. And so our final molecule becomes CH3, CH2, nitrogen, CH3, and CH3, like this. And then naming this molecule here, it's going to be two methyl groups attached onto the nitrogen. So it becomes N dimethyl ethan amine. N dimethyl ethanamine. There'll be no spaces in there. It's just one big long word that we just vomit out like this. And this one up here is, like I said earlier, this is a primary amine, and then this one here would be a secondary amine, so secondary amine. And then the last one down here is tertiary amine. And so how do we make a primary, secondary, or tertiary amine? It's all the same thing. We just react it with an alkyl halide in basic conditions and just let the reaction go.